Well, welcome everyone to another Q-Control webinar. It is my pleasure to be here. So my name is André Carvalho, and I'm the head of quantum control solutions at Q-Control. I've been in the company now for 5 years, and I'm currently in our office in Berlin. And as the head of quantum control solutions, I'm responsible for dealing a lot with our customers and external projects. And today I'm hosting this webinar on accelerating the path to useful quantum error correction. And one of the nice things that we've been featuring in our recent webinars is really sharing the success stories of customers and partners. And it's a pleasure to have with us Danny, VP of Hardware from Nord Quantique. And I'll let Danny introduce himself.
Nice. So hi everyone. Yes, so my name is Daniel Chanskirian. I'm the Vice President of Quantum Hardware at Nord Quantique. I've been the first employee of the company, so for 3 years and a half now. And maybe I can talk a little bit about the company very quickly. So Nord Quantique is a startup company trying to, we're hardware focused company. So we do have theory and all that, but we're actually doing experiments, and the goal is to develop technology on quantum error correction using bosonic codes. Lately we've been focusing on GKP, the GKP code, and this is what I'll be talking about today. This is, and yes, I think an important point is we're situated in Sherbrooke in Quebec in Canada. This is where our head office is. We do have a few people remote, but all the activities is happening in Sherbrooke among a very good ecosystem in quantum. Currently, I'm within the Institut Quantique of University of Sherbrooke. This is, yeah.
Yeah, thanks. Yeah, I guess so to situate people as well, I mean, in terms of the work you've been doing and the topic in general, I guess that this is one thing that at Q-Control we've been thinking a lot in terms of, I mean, as I guess that people that join the webinar already knows about Q-Control and all that we've been developing in terms of software and infrastructure software to help with error suppression. And one of the goals is actually also to help with quantum error correction, right? So I guess that the idea today is to cover your most recent work on error correction, and I first would like to kind of perhaps establish some common background in terms of people know about error correction, what they expect, and what's different from what you've been doing, right? So when people think about qubits and error correction, usually kind of the easiest picture is thinking that you use pretty much redundancy to encode your logical qubit in more than one qubit, and you use this redundancy to correct when errors happen. So your system is quite different from that, right? So can you just tell us a little bit more about, let's say, the history of Nord Quantique and why you chose the system that you're currently work with, and perhaps explain to people what those differences are?
Yes, exactly. So at the start, Nord Quantique was focused in general in bosonic codes. And then it took us just a few months to pick up the right kind of platform, the right code to start with. And the idea of bosonic codes, I'll have one slide on that later on, but the goal is that instead of having this physical redundancy of having multiple qubit and encoding one logical qubit with this, is that we can use a system which has basically more levels, like larger space to work with, and also a simpler error mechanism, error channels. And that system, in our case, it's an oscillator, which is of course very general idea. In our case, it's a microwave oscillator, which is known to have mainly one type of error, which is photon loss. So with this, basically, you can design a code to try to be as robust against this, or in our case, even be able to correct these errors, not only detecting them or preventing them. As you said, you can prevent errors from happening. In our case, basically, the errors will happen, but our quantum error correction will hopefully correct these errors.
Yeah, I guess that this lays kind of the background in terms of the kind of system that you're working with, and I guess that in terms of I don't know if you want to start sharing slides or if you want to bring them up while we are kind of going through questions and discussions. I want to make this as conversational as possible, but of course, I mean, if you feel like you need some pictures to explain a few of those things, feel free to kind of share that. And I guess that maybe we can go straight into the topic, which is your recent paper, right? So so what you've been doing, you just explained, I mean, the difference between the systems, what you're trying to do with those oscillators. We're trying to do the error correction using that bigger, higher dimensional space, right? And recently in your work, you did an implementation of one step of error correction on that line. So what is the, or perhaps just before we go into that, or there's also, so you mentioned the difference between kind of qubits and those oscillators, but also in the world of kind of quantum error correction with oscillators, there's also different flavors of it, right? So different ways that people approach. Can you also kind of say a little bit on that? I mean, what is the difference from, let's say, the GKP stage that you mentioned with other approaches?
Yeah, definitely. That's a good point, which is actually not covered in the few slides I've prepared. So as you said, there's many different bosonic codes that have different pros and cons, if you want. So for example, one of the interesting one, of course, is, and well known, is cat states, which again, within cat states, you have different flavors. So you have, you can have some people call them the free cats. You just initialize the cat state, but there's no like stabilization by itself. And if you do a four-legged version of this, you can actually detect the errors, and then you can perform a correction also. If you just have two-legged cats, then you can detect errors, but you cannot correct them. Then there's binomial codes, which are kind of different. You define the logical states as being superposition of like different types of Fock states that if you do have an error, you can detect it. You go to a leakage state and you can know, and then you can, but it's not always possible to do this correction to go back to your, to preserve logical information. In the case of GKP state, basically what was quickly shown is that actually you can perform quantum error correction, not only like detect that there was an error, but also correct. And this is what we've been focusing on. And in our case, the type of approach that we've kind of took is that this error correction is actually autonomous. So there's no like feed forward needed. So you don't need to get the information out of the fridge, in our case, process that information and send back some controlled pulses that like are depending on the measurement results. In our case, it's all predetermined. We have like a sequence, we just send that to the device, and that autonomously correct measurements. And that's all. I have a few slides on that in the presentation.
All right. Okay. Thanks for that. Also, one thing that I forgot to mention in the beginning, just as a housekeeping kind of comment. So if people in the audience have questions, so please put them on the Q&A button. So just click on the Q&A and put there, and we'll go through them at the end of the presentation. So I see that people are already putting some questions there. So please keep them coming in the Q&A tab. Don't use the chat. I don't think that actually the chat is available there. But yeah, so thanks then for this explanation about the differences between the different bosonic codes. Perhaps I guess that we should go just now straight to, let's say, the actual slides, that so you can present the idea of your recent work, and then we can start kind of showing people what you've done and how you achieved the error correction on those systems.
Okay, that's really good. I'm trying to sharing. Oh no, and it says I cannot share. Sorry, we should have tested this before. Maybe it's because...
And should be ready now.
Okay, that works.
Okay, cool.
Okay, good. So yeah, it's a context like now we want this to have a discussion, but we just need a bit of like visual support and background. So this is really like only 5 slides just to support a little bit like what I was saying before and say a little bit more. So Andre, like, and also if you see questions from the chat that can be fed in nicely with the presentation, that's really good. Okay, so this is just to illustrate a bit what I said before, the idea of using, like, why using bosonic codes. The idea is just like you have this like one physical system, but now that has like way more levels, way more like space if you want to do things. And then in this basically these systems you can encode different states. So here we see the vacuum, of course, the like single photon Fock state, and so on. But then you can also encode more exotic states like the well-known cat state, and maybe even more exotic, the GKP state, often called the grid state. So you can see it, like one way to describe it to like very general audience is this is what you get in phase space if you impose physical, like during pandemic, the social distancing, if you want. So like you can see each dot as some people and just impose social distancing. This is what you get. So the idea of this is that we use intrinsic redundancy from a richer encoding space. And there's basically 2 strategies that you can take. You can say, well, I will encode many qubits within this oscillator. This is one approach which is not so well explored. But the other approach we use is that, well, we'll use this really large space and we'll encode just 1 qubit. But doing so, hopefully we will have some logical redundancy at the single qubit level. That will allow us to do quantum error correction at the single qubit level. If you have a pure 2 qubit, you cannot do quantum error correction. Of course, you need a bigger code than this. So like the simplest you can do, for example, is a repetition code with 3 like physical qubits. There you can correct 1 type of error. But in our case, you will see that with 1 physical system plus 1 auxiliary system, we can do quantum error correction. But there's, of course, it's not free in the sense that we're trading physical redundancy by control complexity. So now, like if you think about the typical transmont-based systems where each transmont can have a readout resonator, sometimes it's shared with multiple transmont, but that's kind of what you have. And then, of course, transmonts are coupled together. But here, each of our building block also has a second mode, which will be a high quality factor oscillator. And this is in that oscillator that will encode our bosonic code, or GKP states. So you need to do state preparation, to do the error correction, and also the decoding. We need to do control on these 2 elements. So the system is a little bit more complex. But the hope is that in the end, we win in terms of like physical resources necessary to come up with a fault-tolerant quantum computer. So a bit more specifically about GKP states. So this is a proposal that is now as 22 years old. Why did it take so much time to come to reality? Well, the initial proposal is infinite energy and infinite squeezing, which are 2 things which are basically impossible to achieve. But on paper, this is really nice because it's one example of a bosonic code that enables quantum error correction at the single qubit level. Another example, which has been demonstrated in 2016, is the four-legged cat, where you can basically use the parity to detect and correct photon mass. I told you, like, the original proposal is infinite energy, but this is relatively straightforward to generalize to finite energy. And there you have 1 parameter that tells you how finite is this energy, which is what we call delta. And throughout the paper that we have, the result, we always use this delta of 0.36 to give you a sense that corresponds to about 3 to 4 photons on average, and a squeezing of about 9 dB. So this is, as you see, this is a quite, like, does not have many, like, it's not like 100 photon state. It's a really low relatively low energy state. But even then, you can see these like opposite logical state plus x and minus x. You can easily distinguish between the two. So like, even though it's relatively small GKP states, logical information is well encoded there. And with this, you can define this, what we call the GKP qubit on this kind of block sphere if you want. So if you're you can see that X and Z states are like exactly identical up to like a rotation in phase space of 90 degree. So what this means that some of the gates will be kind of free to do, so you can just do them in software. However, to go on this y-axis, there you do have some non-trivial operations to do to go there. So like, I won't talk about gates, but if you look into gates for GKP states, some are trivial, some are a bit more difficult, but overall it's kind of the same thing for every system.
Sorry, may I just interrupt there? Just question.
Yeah.
So what you're saying is that, for example, from the X to the Z states is just a rotation that you can do as if it were a frame rotation on the system?
Exactly, it's just frame updating and it's done, yes. Okay. Otherwise, you could just wait for a given time and that this rotation will happen kind of, but you can do it. It's kind of akin to like virtual Z gates in Transmon, where you just update the frame. Okay, so of course this is night. We have night finite energy, but can we still do state preparation of these states? And that has been shown in about 2021 that you can do this with conditional displacements. So what is kind of natural, if you have an oscillator and you just like send energy to that system with a coherent drive, what you will create are coherent states. You displace the vacuum. Conditional displacement is just that this displacement kind of goes in the opposite direction depending on some auxiliary qubit state. And this is, with this, you can see that you can just repeat this thing and create this really like this pattern. This is pretty naively, but it's not too far from the truth. And this has been demonstrated experimentally in 2 platforms, which is kind of nice. So first in trapped ions, given that these conditional displacements are very natural in trapped ion. In our case, we're working with superconducting circuits, and this has been initially demonstrated in Yale and the group of Michel Deboré in 2019 and 2020. In the case of superconducting circuits, these conditional displacements are not as natural, but we have a way to do it. I won't talk too much about this, but if you have questions, you can ask me. So this is about like what are GKP states, how do we prepare them, but we want to do quantum error correction. And the kind of approach, one way to see it is basically like we're doing reservoir engineering. So what it means is that we'll kind of run a circuit that will engineer a dissipator such that basically the GKP manifold, so our logical qubit, are steady states of the system under the quantum error correction, and this even in the presence of photon loss. But then, of course, like that's the main error we have. So even with this, we can, in principle, preserve the GKP states. And in this framework, there's been a remarkable experimental and theoretical progress in the last few years. So I just want to point out to a few other work. So of course, there's all the work done experimentally in Yale, initial work here, and also subsequent work, like really showing really nice results of break-even, and also work in trapped ion implementing kind of the same ideas, but in a different language slightly with a few differences. And also the theoretical work by Baptiste Royer. So what is this quantum error correction protocol? So I told you we can prepare the GKP states with conditional displacement, as well as rotation on some auxiliary resource. That is like some qubit that you have to control your oscillator. Actually, it turns out that the quantum error correction protocol is made of the same building blocks. So we have these, what we call coherent control. Like these are, let's say, ideally closed system operations. We have rotation on the auxiliary and conditional displacement between the oscillator and the auxiliary. And you have 3 sets of those, and we call them just because of how big they are, these conditional displacement, we call them small, big, and small. You can see the first two as being some kind of like stabilizer measurement, if you want, and the last one as being some kind of correction based on that measurement, if you want. But of course, here I'm talking like, if we have a quantum error correction protocol, we do need something else than just coherent control. We do need a dissipative channel. One way to say this is necessary to remove entropy from the oscillator. And in this case, in this protocol, what we need actually is just a reset of the auxiliary. You don't need actually to measure, you don't need to have the measurement result of that auxiliary. So in our case, what we've done in this paper here is that we've demonstrated that this reset, of course, can be done autonomously. This was known before, but now we did it in the context of a bosonic code where you also have your auxiliary is coupled to another mode which has a non-trivial state in it. So it's definitely not straightforward to make this autonomous reset work. Another way to do it is actually do the measurement and then based on that measurement, send a pulse on the auxiliary to bring it back to the ground, to the desired state. And this is what was used in this paper. So this kind of building block, this is what we call the SBS quantum error correction protocol. This corrects for like, if you want, errors, displacement errors along one quadrature. So you can see the GKP state as being like squeezed in both directions. So this corrects one direction. When we want to correct the other quadrature, we just rotate all of these conditional displacement, we just rotate them by 90 degrees, which is again just a software thing. So we implement this. When your qubits are idling, you can do this quantum error correction protocol. And these parameters, these beta and rotations, these are independent on like, is it the first round you're doing or the 10th one? It doesn't matter. These, what we have are round independent parameters. So the initial proposal for this protocol tells you what should be these parameters. But of course, these parameters were determined from like a closed system calculation. So in the presence of noise, in principle, these can be slightly different. So this is what we will be optimizing using the tools provided by Q-Control. We will optimize these operations. So if you look here, you see a protocol has basically like 7 gates, each with a parameterized by a complex number. So in principle, there's 14 parameters to optimize. But what we've done is actually take a step back and think about physically motivated optimization parameters. So we reduce this number from 14 to 3 by this kind of physical motivation. So the first one is that these, like the size of the small displacements depend on the state that you have. So what we do is that we do state preparation of a GKP state with a given finite energy parameter. But this parameter might not be optimal given the noise of the system. So what we allow the quantum error correction protocol to do is to steer this finite energy parameter to the optimal one, to the one that will optimize the logical lifetime. So now what this means is that we're letting these small conditional displacement free to take a different value than what we initially guess. Also, something I said quickly before was that these two small displacements can in principle be have different role. So it makes sense that in principle they might not be equal. In the default protocol they are equal. We're letting them to be free, and this will parameterize just through this ratio between the two. And finally, one thing is that in the frame that we're working, the state rotates with time. This is not a problem, we can keep track of it. But when the auxiliary change state, this rotation will be affected. So what that means is that we need to, in our case, given that we don't have access to the auxiliary measurement results, we need to correct for the average rotation. And this average rotation will depend also on how well the quantum error correction protocol does. So it's really natural to put this as an optimization parameter. So of course, this is what we optimize, but what do we look at? Well, we look at a relatively like involved quantity, which is the logical infidelity. I won't show the definition, but basically like it shows like how much logical information is in your qubit. So if you think about the block sphere, it tells you like on average, all distance are the opposite cardinal states. If, of course, you lose all logical information, everything shrinks to a point and you've lost everything. So we look at this logical infidelity. And this, of course, you need to measure, you need to prepare all cardinal points. So that's 6 experiments in principle. We can reduce this number to 4 given the symmetry between X and Z states. And of course, we want in principle to have time to accumulate errors just from photon loss or through our quantum correction. Of course, it won't be perfect. So we will also induce error through this quantum correction. So we do this, we evaluate this logical infidelity after 4 rounds.
May I just ask a question there, Danny? Because this is really something that comes up quite a lot when we are discussing with people the issue of control, right? So you have your control knob. So those are the degrees of freedom that you can manipulate. In your case, are those displacements, the ratio between those displacements, the energy and the state rotation, and so on. So this is what you can change. But one of the, let's say, the arts in terms of one of the pieces of the puzzle in terms of when you're defining the optimization problem is really when you define your cost, right? So what you're trying to optimize. So in this case here, for example, looking at this logical infidelity was something that you already started with from, let's say, your theoretical model. It's something that over time, when you're playing with your experiments, you had to change a little bit. So how did that happen in terms of coming to that cost function?
Yeah, that's a very, very good point. Yeah, historically, we started by looking just at a single state. And what we realized was that with this, basically, you can optimize if you're not bounding enough the problem, you can optimize the quantum mechanical protocol to correct very well one state, but not others. So with this, of course, like you're not really doing it goes more into state preparation. You can clean up state preparation, like what state you've prepared. You can maybe append some of these like tether tune rounds of quantum correction to kind of clean it, but it's not general and it's not useful for performing actual quantum correction on the state that in principle you don't know. Otherwise you're cheating. So historically we started with this, but then we forgot that kind of it doesn't work. We need to look at something really that encompass all the logical information we have, and this is where we came up with this using the logical infidelity as the cost function.
Thanks.
Yeah. Okay, so given this problem, we need, of course, to choose an optimizer. In our case, we're here because we use Q-control, Boulder Opal, namely, and even more precisely, we use the Gaussian process optimizer. And this optimizer, if you look up at even on the Q-control website, there's like a decision table, a decision graph that shows you do you have a good model for the system? We do have simulations, but we don't want to rely on simulations because simulations are quite heavy on such a system. So let's assume we don't have a model. Then basically, can you do closed loop optimization? Yes, we can do that. Do you have many parameters to optimize? Here we reduce it to only 3. And in that case, the recommended optimizer is a Gaussian process. And it's an optimizer also that we use in very different contexts, and it worked quite well. Maybe I could really quickly say that there are other ways to do this type of optimization than Boulder Opal, of course. But what we've done is that on a simpler problem, which is basically just optimizing these auxiliary rotations, we've compared quite thoroughly this optimizer from Q-control and an open source one. And what we've seen is that the one from Q-control converged to better results slightly faster. So on this simpler problem, this convinced us that we'll just use it for this problem. And in this case, given that the experiments are quite involved and a lot of things can drift over time, it's a little bit too, we didn't do this one-on-one comparison for this system, but we did it on a simpler problem. And Q-control was there.
Of course, I mean, I had to kind of thank you for actually explaining that, because it's something that we usually do ourselves, kind of doing benchmarks and hearing that one of the customers actually did themselves and kind of found these results is, yeah, so it's quite reassuring for us. Yeah, pretty nice to hear.
Yeah, and for us it happened kind of naturally. We had kind of let's say a side system, a test system that was kind of just idling. We were just running that in the background. We look at the results good. We included, we kind of just transitioned very quickly to Q-control in our main experiments, and that worked very well. So far I've been like, this could have been a theoretical talk until now, but now I'm like going back to actually showing you some of experimental results on the actual hardware that we have, which is quite common in superconducting circuits for bosonic codes, which are these three-dimensional coaxial cavities, where you can get really easily about 1 millisecond lifetime. If you work even more, you can get even more than that. But of course, this is just US area, and we have this auxiliary transmount that we kind of introduced from the side that is very weakly coupled to the oscillator. So if you just jump right to the result about this optimization, we look at this cost function, which is the logical infidelity. And you see here the infidelity is quite large. This is kind of more or less by design, the sense that we want to have errors we want errors to have potentially accumulated. And what we see is that through iteration of this optimizer, we can decrease the logical infidelity. Here, this is not ideal because this first point is not from this default protocol. It's from a previous optimization. So it doesn't show you that the gain is actually larger than that. So one way to look at this data differently is to look at the 3 different parameters that we've optimized. And we look at the cost function for all of these 3. Of course, it looks like all the points here, it looks like a mess, because even for like, if this parameter is optimal, some other parameter can be completely wrong, and that leads to a very large cost function. But if the cost function is very low for that parameter, it must mean that this parameter is not too far from optimal. So this is kind of, we can guess from these kind of, these bars just show the minimal value within each bin. And from this, we can get an idea from the landscape, cost function landscape. And we see relatively well-defined minima in this case. And here it's something a little bit less pronounced, but definitely we did gain something from going away from the default protocol. And if you think about just doing it brute force, just sweeping all 3 parameters, here there's only 1 grid iteration. If you divide 1 grid into a cube, you will see that your resolution will be very, very low. So even this, like these gauge grain spinning, this is actually corresponds to way more than 1 grid iteration if you would do the sweep naively. So definitely there's gain into using this optimizer, or any optimizer in this case. So last slide, I just want to show you the kind of end result. Did it work? So here what we're doing is, you can call that a quantum memory experiment. So we're encoding our state. So we're doing state preparation. Then we're doing quantum memory correction for a given number of rounds. And then finally, we're kind of decoding back to the auxiliary to perform the readout. In this case, we can call that tomography. And what we have is this logical fidelity now versus time. Each point here corresponds to 1 round of quantum error correction. So you see that we work in a regime where actually we're not doing the quantum error correction very often. This is basically, given the noise level of the system, there's an optimal rate of quantum error correction. If you do it, given that this error correction protocol is not ideal, it will also introduce error as well as correcting. So given the noise level, there's an optimal rate. There's something that could be optimized. In this case, it was like roughly optimized. It was not part of the closed loop optimization. But basically, we do like the quantum error correction like in 4 microseconds, and then we wait for 10 times longer than that before doing the next round. And what you see basically is that if you just look at the logical lifetime extracted from this decay of the logical fidelity, we see that if we do the default quantum correction, it looks like you're not doing anything, which is always a bit like weird, but it's just like it happens to be that way. But through optimization, we gained 15% compared to not doing anything. And given that doing the default and not doing anything are almost like equal, it also translates to a very similar number for the gain that we get from quantum correction, which is in this case 14%. So this is what I add. Like the bullet points is that we take home messages, if you want. We perform autonomous quantum correction of the GKP qubit. And closed-loop optimization was critical for us to achieve this kind of milestone for us of like doing something that starts to correct more errors than it generates. And this might seem a little bit stupid at first glance, but this is actually something quite hard to achieve, especially in systems which use like a brute force physical redundancy. Even the best system are just starting to get this gain from quantum error correction. In our case, we can achieve it with a single qubit.
All right. Okay. Yeah. Thanks, Danny. Yeah, that's really nice results. Guess there are some questions coming on the Q&A, and I also have some questions myself. So people, please keep bringing them in. So there's one here saying that it sounds like photon loss is your main error. Could you comment more on how your dissipative stabilization differs from some of the related cat qubit implementation? I guess that you mentioned a little bit of that in the beginning, but just and the question continues, where forcing paired losses instead of single losses become the stabilization mechanism.
Yeah, that's a very good question, and it's not something that is really trivial to answer. So yeah, if you think about stabilization, so like you do something that kind of like keeps you can like think about it as a potential well, you keep your states there. So it looks like you're preventing errors from happening. And I think this is kind of what's happening with like stabilized cat state with this dissipative stabilization, is that you're preventing errors from happening in the first place. In our case, it's kind of the same, but given that the stabilization is kind of more like digital, it's kind of like we apply it. The error could have happened before, and then we can correct it. It's similar, but also different in that sense. Hopefully this is adequate. If not, the person is welcome to ask for more.
Sure. There's another one about someone that's working on quantum error correction, and it's asking if you could tell about stabilizer formulation and 313 stabilizer code. I don't know if this is to detail, and how stabilizer operators correct quantum error. I think you briefly mentioned stabilizer in one of your slides.
Yeah, exactly. So so the GKP code is in principle a stabilizer code. You can see the quantum correction from a completely different formalism. This is what was done in the latest paper by Yale. But if you look at it from the stabilizer formalism perspective, what we do with this, let me come back to this slide. So that's one slide before. This protocol, you can see it as a stabilizer measurement. How do we see that? So, well, this big displacement, this is actually, let me go back to here. Okay, so the stabilizers are basically like these points here in phase space. So these are always, if you want, red in this picture. While the logical information is halfway there. So here you see for minus x, this point is blue, this one is red. Yes. So the stabilizers are basically like you need to go measure here. Is it red to correct? Like, is it red? That's the question you can ask. And if you add the displacement error, then it won't be, you won't get the value, you won't get the correct stabilizer, you won't get plus or minus. You won't get +1, sorry. You'll get something else. What happens is that, so this is mainly this displacement serves as a purpose of like getting to this point, if you want. Then why is there another small displacement before? Well, this is because we're working with finite energy states. And in that case, so only this big displacement, you can see it as an infinite energy measurement. You prepend this with a small displacement, which is like in quadrature, and that corrects for this finite energy. And you can see these first two blocks as a finite energy stabilizer measurement. But you have not done the measurement yet. The measurement is done later on here during the reset, where we don't get the measurement result, but an actual projection is done on the system. And then the last conditional displacement is kind of a autonomous correction based on the measurement, but this is done kind of all within the protocol. Good. So
I was muted. Okay. Yeah. No problem. So I guess that one other question that I want to ask, and also to give a bit of context to people that have not come across with Boulder Opal, that's our software that Danny was mentioning, is that it is our software is our product for experts, really, like Danny and others, and researchers that are actually trying to do optimization simulation. And in this case, Danny was showing about how to do the closed loop optimization. One thing that happened, that actually there was a paper recently also doing GKP states, that was the group at the University of Sydney, and they were looking at, it's a totally different system, right? So it's trapped ions. So in that case, the motional modes plays the role of your resonator in your case, right?
Yes.
And then they used one other control strategy, which is using the model and designing, for example, a pulse to better prepare the systems. And in this case, for example, what they did is that they used some of the features in Boulder Opal that you can design robust pulses and better pulses. So I guess the one question that I have is that in your case, you use the closed loop to actually tune some of those parameters. Do you have any plans for the future to use something that you could, for example, replace some of those gauge-based implementations to something like a continuous pulse, or do some optimizations in that direction?
Yes, definitely. This is something that is ongoing currently within Nord Quantique in the theory team. So this is something we can test, given that we have numerical summations that are like not as quantitative as we want, but definitely like close enough, within 10% of the experiments. So we can use these simulations to test strategies before implementing in the lab. And this is something we're currently looking at, optimal control for the state preparation. Right now, we're using an approach where state preparation is done with these kind of gates that we themselves calibrate very well. Then the parameters of these gates are determined from a closed system optimization, which is done before doing the experiments. But definitely, this is something that we're looking into, bringing this type of optimization in experiments.
Right. So yeah, we already kind of almost 50 minutes here, but I guess I want one other question here in terms of that for us, it's also very important in terms of this distinction between error suppression and error correction, but also in terms of okay, so the question is in terms of threshold. So when you think about quantum error correction, you usually think about the error suppression is trying to lower your baseline error rate, right? So that it can make the error correction easier. So does that picture maps easily to your protocol and the way that you do things there? Is there a threshold? How does kind of minimizing the initial error by error suppression helps in the error correction mechanism?
Yeah. So there's not I'm not completely sure, but I don't think there's a threshold per se. But if you look at the original proposal for this SBS protocol, so this paper here by Baptiste Royer, you do show that the logical error with quantum error correction does go down when, of course, you reduce the error at the physical level. which is mainly when you reduce photon loss. So definitely there is a gain that basically like not only you want to improve the way you're doing quantum error correction, but you also want to improve the physical systems yeah. And this is kind of the main difference, one of the main difference we have, for example, with the recent paper from Yale, where the physical systems just happen. Okay, so the cavity we can have way better than what we had in the paper, just that this is the paper, this is the device that we had everything working. For the transmont, this is like we're just starting to get these transmonts working with our in-house fabrication. So it was about like 10 times worse than in Yale. So definitely that introduced way more errors through quantum error correction. So all this to say that our gain that we get is 15%, 14% is definitely limited by the physical errors that we do. And currently what we're trying to answer is how much is it limited by control errors? Are we doing what we think we're doing? Are we a little bit off? And even if we're doing what we think we're doing, can we do something better? And this is where optimal control can really help.
Right. Okay. So I have one last question before we wrap up. So there's one question here in the chat asking, can you provide insights into the key challenges or considerations into optimizing the parameters of the quantum error correction protocol for GKP states, and how the closed loop optimization with Boulder Opal contributes to achieving effective finite energy parameters?
Okay, so this is, so the key challenges, let me just, I need to read the question again. Okay, so in our case, as I told you, as I told everyone, we decided to reduce the number of parameters to optimize, given that these experiments are, in our case, it can be fixed, but in our case, experiments are relatively slow. So we definitely we constrain the problems. So that's a challenge. Like, is this constraint too large? Again, you do need to constrain a little bit the problem. Otherwise, you might do you might optimize something very specific, but then it will fail in every other instances. So this is definitely one of the challenges and consideration that we need to take into account. As the second question is basically like, I think I more or less answered this in the sense that definitely you can do closed loop optimization with other tools than Boulder Opal. What we found was that on a simpler system, it outperform, and that really, in our case, given that the length of the experiments, it really helps that if we can converge quickly, then we can run this optimization in a real system more often. And about the question about effective finite energy parameters, this tells us, like, let's say optimizer push us to like a different number. This tells us that we should have prepared that state initially. But this is not the path we took for the paper in the paper, but this is definitely something that if you, given the noise system, you find that you're not initializing the right size of GKP state, you should change that size, definitely. So like here, given that we cannot have a simple model of the system, it's quite complex, we can use the experiments actually to learn something and then change that after.
Yeah, this is one of the fascinating things that I find about using the closed loop and actually using the experiments to inform you about things that you didn't know. And it's nice to see how you learned a little bit about your initialization from the results to your optimization. So exactly. I think that it's time to wrap up. I don't know. Thanks, Danny, very much for coming and presenting to everyone about your recent work. Is there anything that you'd like to say or?
Yeah, I mean, thank you very much for having us. Yeah, we really enjoyed working with Q-Control. It was quite easy to use. We just had to experimental is like, we had a Python environment. We had to update a few things in Python environment to make it compatible with Q-Control. It took 5 minutes and it worked right away. I encourage people to look into it. And also to, of course, make their due diligence by also looking at if everyone kind of do this comparison and everyone comes up with the same conclusion, it just makes for a stronger conclusion. If you're interested in our work, of course, I invite everyone to look at our paper. We'll also be presenting brand new results at the March meeting in March. So I invite everyone to come to see us and talk to us.
All right, we are looking forward to it. Thanks a lot, Danny, and thanks everyone who came and to watch this webinar. Thanks, everyone. Bye.
Thank you.